Next up, we have electric fields. And what is an electric field? It is the experience of a force on a particle, a charged particle, let's put that, at a distance from another charged particle. So it's the thing that one of the particles is emitting in the space around it that causes a force to be on another charged particle. And the way that you measure these, they are measured by placing, and this is theoretically, not actually done, measured by placing a small charged particle near a charged object and measuring the force on it. So in real life, the way they would see this is they'd take something like an electron, they'd put it near a charged object at a known distance, and then they would see how fast it accelerates at that point. Now, there's a lot of weird calculus you have to do because it's getting force added as it moves. So for us, we'll just think about it at an instant in time what the force a charge would feel would be. So these are very similar to gravitational fields in that Coulomb's law was like the force of gravity. These will be like the gravitational field. So if you remember, gravitational field is equal to Gm over r squared. This one is going to be the force of an electric, well, here's the force of electric. K Q1 Q2 over r squared. What we can do with this is turn it into electric field in two different ways. One, electric field is just going to be equal to the electric force over a charge, or we can write it as the electric field KQ over r squared. Either one of these works. If you know the force, you can just divide it by your charge and you can figure out how strong the electric field is. If you only know the charge of the initial object making the electric field, what you'll do is Coulomb's constant times that charge and then the distance away from it. That'll be the strength of the electric field there. At this point, normally I would show some demos in class using a Van de Graaff generator so you can see what electric field lines are. But we'll have to do that next time you're in class. So for now, if you want to look some up online, they're pretty neat. Look up like Van de Graaff with hole punches because that's the demo we're going to do. We're also going to do stuff with like aluminum foil, but we'll see when we get there. But for now, let's go on to talking about electric field lines. So an electric field line is a representation of how a positive, this is important, don't get this mixed up on the quiz, I've seen it happen before. So it's a representation of how a positive charge would move in an electric field. And the closer the lines are together, the stronger the field. So when they're densely packed together, what you would see is a really strong electric field. When they're more spread out, then it's not as strong of an electric field. Now there are three rules that we have to pay attention to when we draw our electric field lines. Actually, I think there may be four. So here are our rules. Number one is that lines point from positive to negative. That makes sense because they're showing us where a particle would be traveling from, a positive particle. Positive wants to get away from positive. It wants to go to negative. Rule number two is that the lines are proportional to field strength. Meaning if I have a charge that's double some other charge, it's going to have twice as many field lines coming off of it. Number 3 is that when lines are close, your field is stronger. If they're densely packed together, then that's going to be where your field is the strongest. So if you think of a charge as like a point, when the lines spread out from it, close to that charge is where your electric field is going to be strongest. Furthest away, it's going to be weakest. That makes sense because you'd expect more force close, weaker as you travel away, exponentially dropping off as 1 over r squared. And finally, field lines never cross. So let's see what this looks like when we apply it. Here's number 13. Let's say I've got a charge here of, I don't know, let's say 2 coulombs, positive 2 coulombs. And then over here, I have a charge of positive 4 coulombs. Now, field lines that come off of these never want to touch. They don't want to cross through each other, and it always wants to go from positive to negative. Since these are both positive, they just want to go to infinity because infinity is the closest thing to negative. It'll be 0 field strength at infinity, so they want to go over there. Let's say that I make each coulomb of charge equal to 2 lines. So this one should have 4 lines coming off of it. This one should have 8 lines coming off of it. So what I'll do is I'll just draw 4 lines. I'll have 1 coming off there, 1 coming off there, 1 coming off here, 1 coming off there. So these ones want to get away from that. But since they're further away, they won't bend as much. So I'll have a field line go like that. Remember, going from positive to negative. Proportional strength, so this one should have 8. Let's go 1, 2, 3, 4, 5, 6, 7, 8. Okay? I'm going to do the same thing with this one. 13 gets in the way, but you get the idea. These ones are going to be really repelled by this, so they'll actually get curved backwards. Same idea over here. Curved away. Curved away. This one in the middle, if it was perfectly in the middle, it's just going to bend back on itself or come 3D. But let's say it's just slightly above the center. It'll go like that. These ones down here getting curved away. Curved away. There we go. So that would be how we draw our electric field lines. Now what I want you guys to do, I'm going to go ahead and erase this up here so we have some space, but I'll leave up the rules while you work on it. I'm going to give you 2 more examples that I want you to try out. This is still part of 13. Let's say I have negative 3 coulombs on this one and positive 2 coulombs. That'll be one example, and then I'll do another example down here. Actually, I'm going to get rid of the rules. You should have them written down. And on this one, we're going to have 3 charges. In this one, I've got positive 2 coulombs, positive 3 coulombs, and negative 3 coulombs. So what I want you guys to do is, using your rules, figure out how the electric field lines are going to look on these. Pause the video, and we'll be back in just a second to go over them. Okay, so let's take a look. On this first one I did up here, remember each coulomb of charge is equal to 2 lines. So I have 4 lines coming off my positive 2 coulombs, 6 lines going onto my negative 3 coulombs. Remember, lines point from positive to negative. So you notice on these, they come off. I just chose like a 90-degree angle that's offset from vertical by 45 degrees. So I've just got 4 coming off. As they go, they want to curve towards the negative. So they come straight off the positive and curve towards the negative, both sides. This line whoops around here. This line whoops up over there. So all 4 of the lines from my negative or my positive 2 go over and connect to my negative 3. On my negative 3, I need 2 extra lines coming to it, so I just have 2 lines coming from infinity curving in. That way all of my charge is conserved. Down here, this guy should have 4, this guy should have 6, this guy should have 6. So in this, what I did was half of the lines on this one, and about 2/3 of the lines on this one go over and connect to that one. That gives me all 6 lines since it's negative. I just have 2 coming off over here, 2 coming off over there. Remember, it's curving from positive to negative. It wants to take the straightest path in that curved space. Yeah, there you have it. Electric field lines.